Okay, Denise.
Hey everyone, happy morning. It's still morning, huh? Yeah, 11 a.m. Good morning. Happy Tuesday, everyone. Welcome, welcome. I love the love in the chat.
Good morning.
Good morning. I know that must be Danny, right? Good morning. It's nice to hear good mornings, y'all. All right, I'm gonna go ahead and get us started. So if you haven't yet, please make sure that you go to Google Classroom, make a copy of today's slides. We are on day 5. So day 5 is where we're at. And more so, you can follow along, take notes if you need to annotate on your slide. You know, that's the reasonings for that. All right, so let's go ahead and jump into our check-in today. I like today's check-in because you'll see. Okay, so here we go. What is your favorite method of laughing? We got belly laughs that come straight from your stomach, and it's hard to fake that. You got giggling. You got the snort laugh, which I tend to do. You got the out of air laugh, where it hurts so bad and you're out of air. And what else do we got? The scream laugh. I added that because that's what me and my siblings like to do, scream and laugh. So different kinds of laughter. Hey, there's maybe one that I missed in this list. Here's just some examples. Go ahead and put in the chat, and I already see some in the comments. What is your favorite method of laughter? All right, and then I'll check attendance from there. Okay, we got some stuff. And then good morning, Rob. We got the out of air laugh. We got the cry laugh. Thank you for adding in the cry laugh. Yes. We got a lot of out of air. We got all of the above. Okay, we have fans of the out of air laugh. You know, that's when you're laughing and you look silly, nothing's coming out. My laugh is a mix of them. It's so bad. I think likewise for me. We got the giggling and the out of air. We got another for giggling. So let me tell you all. I think okay, so I shared this question, and my favorite laugh, I think, was the scream laugh. So I love just, everybody screaming and laughing at the same time. But I got convinced that the out of air laugh is the best because it's like so funny that your air is gone. And the reason why I didn't choose out of air is because it hurts. I don't know about some of you, but it hurts my stomach when I'm out of air, and it's just so painful, but it's really so funny. So, and then what's a belly laugh? I see that like a Santa Claus, when he's laughing from his stomach, like it's coming from your diaphragm kind of laugh. That's what I mean by a belly laugh.
You see, but that's the thing about out of air laughs, though. Out of air laughs resort in crying laughs
Yeah, I think so too.
because that's how funny the joke is. Like, it's so funny, it hurts to laugh. You end up dying laughing,
Yep,
and that's why tears start to come out because that's just how funny it was.
I think so. I think so, CJ. That is eloquently explained. I think yes, I am convinced. Awesome. Okay, we got a mixture here. Out of air, screaming, and the crying. Yes, those are the best. And I don't know if it makes you think about the last time you laughed like that, but it totally does for me. It makes me want to just laugh again. Um, Awesome, everyone. So thank you so much for sharing. Let me go ahead and see who we're missing here today, and maybe y'all can help me. And if I accidentally call you out as absent, please correct me. So I did that super fast. Okay, so this is who we're missing, everyone. I'm missing Jalen. If you're here, please let me know. I'm missing Miles, Rebecca, Carlos, Risha, Leon, Sincere, and Celia. So double check me on that. I'm gonna go ahead and repeat it once more. Awesome. Welcome, Jarrell. I see ya. Okay, so this is what I'm missing. I'm missing Jalen, Miles, Rebecca, Carlos, Risha, Leon, Sincere, and Celia. If you're actually here, please let me know. If you're friends with these folks, please send them a text to come on into class. We got some credit today. Got a lot of interactive stuff to get the learning going, all of that. Thank you so much for this check-in sharing, y'all. Oops, LOL, this is happy Monday. No, y'all, it's Tuesday. So, yes, happy Tuesday. We made it through Monday. Let's just think of it like that. Okay. Oh, good. We got a few more folks coming in. So let me fix up my attendance. Awesome, awesome. Glad y'all are here. All right. So let's jump into what we're doing today. So what in the world are we doing today? We just took attendance. We're going to continue our discussion that we started off on Thursday about unit circles and raves. So if you recall, there was some group work. Y'all had amazing stuff. We're going to come back to that. We're going to finish up like how in the world is a unit circle connected to waves? We're going to talk about that. There's going to also be a Google form for you to kind of process your understanding about what I talk about today. And lastly, we'll have a checkout. And asynchronous number 10, everyone, I pushed back. Instead of it being due a typical Wednesday, it's due on Thursday today. Now, I did reach out to some of you who are missing asynchronous number 9. And I want to also share with y'all, I forgot, no, I didn't share this because I'm just seeing you now, but I want to share with y'all that I'm actually at the school and I am doing training for hybrid learning. I get actual students here next week. So, but because I'm doing training, everyone, my office hours aren't available this week. So this is what I'm going to do. On Thursday, I'm going to be holding extra office hours from 2 to 3. And so if you're missing asynchronous number 9, I'm going to reach out to you so you could join me in my office hours so we could check in. So just a little bit about that. So be on the lookout for an email. As well. Oh, okay, cool. Maria's saying, sorry, I'll turn it in today. Hey, just letting you know, I just want to make sure that I'm being supportive because I know I'm doing this training and my office hours are being taken up for this week. So I'm offering extra ones on Thursday to help support you all. Okay, some of you did it before class. Okay, I'm excited to check it out. But just a little update on that. And our next one is due Thursday, so there's some time to take a look at that next one. Okay, everyone. Thank you so much for all of that. Cool. Let's go ahead and jump on in. So, unit circle and waves recap. So first, let's do a little recap. Sorry, I really like your. I really like Rob's photo there. I did not know you could do, or you had that hairstyle. That's awesome. Okay, so here we go. So last week we had this essential question. How is the unit circle connected to functions with waves? Remember this? Y'all did some group stuff. We were asked this question and you all were trying to figure this out. And we had an amazing stuff. And I know I was with the group last week. So that was a review of what we did. I know, right? In the picture. So that's what we're jumping into today. We're going to finally know the answer. Okay. I went ahead and I took a screenshot of the responses that each group had. Now, I took a screenshot with your name still anonymized. So just so you know, this is legitimately your responses. You all went on Desmos and there was this tool that kind of was mapping out how a unit circle or a circle makes waves. And you all were asked to kind of try to figure out the connection. So we have Maria's group says, as a unit circle turns counterclockwise, so opposite the way clock moves, the waves advance. So the more turns you make, the more waves you got, is what Maria's group had said. Grace's group said the higher the number, the bigger the curve. Another way I think they rephrased it is the higher the number, the more waves. So that looks very similar to what Maria's group said. So the more turns you make, the more waves you get, okay? Then we have this, when moving the bar from left to right, it creates a wave due to the triangle. So this group kind of noticed something about triangles and degrees. Lastly, Vivian's group says, it looks like the line grows up as you go around the unit circle, very similar line of thinking to other groups. And you could use the length outside of the circle to find the length of a wave. There was a little question about that. Then we have maybe each time the line goes around the circle, so each time this happens, it equals a wave. So that's very interesting thoughts that y'all had last week in your groups on Thursday. So a little refresher on that. Amazing. All of you were on the right track. So all the groups were on the right track when you were doing this notice and the connections between the two. Let's finally learn what is the connection. So how can we create waves with a unit circle? That is our essential question that we're going to answer today. So let's see. Okay, unit circle and periodic functions. So again, feel free if you want to go on the slides with me, but a sine wave, y'all, is formed by imagining a point on the circumference of your circle, like on Desmos, and you trace the vertical height of that point over some input such as time. So try to read that again to yourselves. I just read it, but go ahead and reread it, right? There's a lot going on in this. There is mentioning of circumference. Let me underline that. And there's mentioning of something of a tracing the vertical height. What do they mean by vertical height? And it says you have some input such as time. So let's make sense of that. And I have a little visual for you to help us make sense of that. All right. So that is the answer, everyone. So first off, y'all were trying to figure out how the circle makes waves. This is the answer, but let's figure out why this is the answer. What is this saying? Okay, y'all, I have a scenario for you. Ferris wheels. I know, hopefully we've all been on a, well, not hopefully we all know of a Ferris wheel. Not that we've all been on one. So let's say we have a Ferris wheel. And let's say that on this Ferris wheel, you enter in at the bottom. Now, I live in Hayward, y'all. And one thing I miss after COVID started was we would always get every October and every springtime, there would be a fair that would set up in Southland Mall in Hayward. And they would always have a Ferris wheel. And I loved going on the Ferris wheel. But anyways, over at the Southland Mall, how you would board the Ferris wheel was actually right at the bottom. So you would board right at the bottom. You have to get in quickly. So let's imagine that it's that very same Ferris wheel where you get on at the bottom. So you board it on here. Okay. And over time, right, you know that as you get on the Ferris wheel, you're gonna start at a height of 0 and then you're gonna go up. You just go up, 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 and you're gonna keep going higher and higher, right? Now I'm just pushing my, there we go. There we go. So I boarded here, right? Our board's here. Over time, right, you're just gonna go around and around on this Ferris wheel. Let's imagine that over time you end up here and you're the rider. What is the height when we're talking about traces the vertical height? Take a look right here. It's gonna pop up. So right here, imagine that I'm trying to measure my distance from the ground, my distance as the rider to the ground. Like, what is the distance? Take a look here. It's coming up. Height. When I measure my height over time on the Ferris wheel, I get a wave. So that's how we could put this into context. Now, I want to also point out something. So let's say I'm on the Ferris wheel and I go all the way to the very top. Let's say I'm all the way to the very top. This very top part means I'm at the highest point that I can possibly get on the Ferris wheel. That means I am at a maximum point when it comes to the wave. So take a look. I started at a height of, I guess let's say it's meters. I started at a height of 0 meters. I go up the Ferris wheel. I reach my maximum height. Then my height is going to decrease because I'm going back down to my original starting position. I'm going back down. So back down. Until finally, I'm back to where I boarded. I'm back to a height of 0 where I boarded. And it looks like on this particular Ferris wheel, it took 3 minutes for me to get on the ride, go around once, and come back into my initial starting position. It took 3 minutes. Take a look at how this wave correlates to the graph now. What we're doing is we're mapping my height over time, or we're calculating the distance of that point over time. Sometimes it's not height, sometimes it's something else that we're measuring, but according to this image right here, it's height. So that is the actual connection. And what I have for you is actually the tool. So let's say my explanation with my little drawings is not enough, right, to convince you. So I'm gonna go ahead and clear my screen and show you the tool. So let me escape. Sorry, y'all. And here's the tool. I'm gonna also share with you the tool so you can explore this as well and check it out. Oh, sorry, Danny, I just saw your comment. I remember wanting to go to the fair at Southland, but my fam always went to shop, not for the fair, and then being dead. Yeah, yeah, as a kid, yeah, but then now, dude, as an adult, I go on the Ferris wheel, making up for all those times I couldn't go because my parents just went shopping. So I'm with you. Okay, y'all. So take a look. When you open up this little thing I just shared with you, you have this cool Ferris wheel app, I guess you could call this. What I'm gonna do is I'm going to move this all the way to say 0 minutes. Oops. So initially you're not at a height of 0. I guess you're at a height of 1.5 meters. So I guess there is some. You probably have to stand on something to kind of get it on the ride itself. So that's okay. Oops. Now, below this, you have the graph. Notice that your input, your x-axis is in minutes and your height is in meters. So take a look. So as I move this dot, as the time goes on, your height increases. Oops, oh my gosh, I don't know how to do this slowly. And as I'm moving it, notice how your height over time is getting graphed down here. Let me try to zoom out to see if you could see this better. Yeah, it won't let me. But yeah, you all have the link, so take a look. So you go around once, almost once. I have to get myself to, can I type it? No. I want to get back to, there we go. So I'm back to my initial position. Notice how that is equivalent to one wave. What we call this is basically, it's one cycle. So I went through the Ferris wheel once, I did one cycle. That's what it looks like here in the wave because I graphed my height over time. Let's say I go around once more. Right? Because it would suck if I had a Ferris wheel that only went around once. You want to go around at least 3 times, right? So this is me going another round. Notice how you started at a height of 1.5 or 0, whatever you want to think of it. You go up to your maximum height, whatever that is. It's going to be like about, it looks like it's about 175 meters if I'm making an estimate. You go back down to your starting and then you go up and then back down again. So this is me doing 2 cycles on the Ferris wheel. Then we can keep going. And another 3 minutes. And it looks like I did 3 cycles now. And I did 3 cycles over 9 minutes. So notice now how a circle is making waves if you map the distance of the point to the ground, specifically in the Ferris wheel. So that is actually how a circle makes waves, everyone. So that is the answer to the essential question. And this Ferris wheel is used as a visual to help you make those connections. So that is the answer to that big idea that you all were investigating and grappling with. Let me pause. Let's see. Are there questions about this? Let me just bring this back up. Let me pause for questions. And if there's no questions, we'll continue to go ahead and talk about this. And we'll have a Google form to check your understanding about this. Okay. If questions come up, do not hesitate to ask me. Let's go ahead and transition to slide number 8, y'all. Again, we are on day 5 of our slides. Slides are linked on Google Classroom. Okay, everyone. So functions that model these kinds of wave-like behaviors that we just saw with the Ferris wheel, they're called sinusoidal functions. That's a weird word, right? And sinusoidal functions are either sine or cosine functions. Take a look at how they're graphed here. Cosine is basically like a sine graph, except it's kind of just shifted to the left a bit. Take a look, cosine's in blue, sine is in yellow. I also want you to notice that your input can be radians, or it could also be degrees, or it could be time, like it was when we're looking at the Ferris wheel, remember? So it could also be time. It could be whatever the input is. So sometimes your input could be how many degrees you went around the circle, how many radians you went around, or it could be time like the Ferris wheel. So that's the only difference. Again, sine and cosine, they're known as sinusoidal functions. These are the two kinds of waves you can play around with. Next, let's go on to slide number 9. Unit circle and periodic functions. So periodic must be a new word for y'all. So what are periodic functions? That's going to connect to our big ideas, because periodic functions are functions that create a repetition of values at regular intervals. So that's the formal word. One period or a period is the length of one of those intervals. So what I have for you right here, 2 examples of what we call periodic functions, because they repeat over time. Visually, it repeats like a wave, or it repeats like this, where it kind of looks like ghost heads repeating over and over. Different kinds of periodic functions. And y'all saw some of these on that decimal activity as well. And then Danny puts the 2 points back and forth. So do you mean 2 points? I'm not exactly sure of the question, like 2 points back and forth. Not exactly sure, but I will right now on the next slide talk about how we, I believe, find period. Let me know if you want to rephrase your question, but. I appreciate the clarifying question. Oh, okay. Don't worry. I'm going to continue to talk about it. If your question comes up again, try me again. It could be just me. I sometimes have difficulty interpreting questions. So y'all, what is a so a periodic functions have something called a period. That's why they're called periodic functions. They have things called a period. Now, what is this period that I'm talking about? A period is basically the length and time that it takes for a wave to repeat its cycle. That's what it is. So y'all remember the Ferris wheel? When I boarded the Ferris wheel and I went around once, that would be 1 period. So in the Ferris wheel example, it took me 3 minutes to complete a period. So my period length for the Ferris wheel is 3 minutes. Let's talk about the period for a sine function. So a function has period p, we just call it p, if, and this is the formal definition that y'all will see in textbooks. Don't worry, we're going to break it down right now. It says if f of x plus p is equal to f of x. That means after a certain p, you're going to get the same output values, is what this is saying. And it says for all values of x and x plus p in the functions domain. So for sine waves, everyone, the sine wave has a period length of 2 pi. Notice how it starts at 0, does 1 cycle, returns to 0, and it does this after 2 pi, radian length 2 pi. And then after, it keeps repeating this cycle over and over after every 2 pi. How I would write that using the formal definition is that this function, sine, is periodic because my p right here in purple is basically 2 pi. So now we know that the sine function is a periodic function. Its cycle repeats after every 2 pi radians. So that is what a period is. Let's see if there's questions about this and about the period for a sine function. Okay, I don't see any questions coming up for us. Again, you will have a Google form so you can process all of these slides that I'm going over right now. But if questions come up, please let me know. And then, yeah, so let me go ahead and acknowledge right now at this point, if you're like, oh, this is kind of a bit, don't worry. The point of the Google form is for you to process as well your understanding. It's not to grade you, as in kind of grading whether you're right or wrong. Absolutely not. So, more so, the Google form is for you to process, and it's information for me so that I know where you all are at. So, that's what the point of the Google form is. But again, if questions are coming up, please ask. If you're able to develop a question, but perhaps some of us are at the point where we're still processing all this information, and that's okay too. So I want to just make sure I put that out there as well. So let me just go ahead and see what we got next coming up for us. Okay, y'all. So I went ahead and I talked a little bit about the rules on how to find the period, right? Some of you had a bit of questions, and I think some of you had difficulty in expressing the question. Um, so, how about we do an example with the Ferris wheel again, something that we kind of are familiar with? Let's do this. Let's do an example to see if, with an example, if we can clarify your understandings. So, our goal right now in this example is find the period of the Ferris wheel. Period. Periods are important in periodic functions because a period means it's the length of time that a cycle takes to complete one cycle. So let's do this, y'all. Let's see, in the chat, how long does it take for me as a writer to start at the bottom and then go up back to my initial position? If you remember, how long did it take when I was on the Ferris wheel? Okay, so Danny put 3 minutes. Brenda put 3 minutes. Now, and then we got, okay, so we got a solid, okay, cool. Yes, y'all are saying three. So is anyone able to explain why it's 3 minutes, either with the Ferris wheel or the graph? Like, how do you know that it takes 3 minutes for me to complete one round around the circle or one cycle? I don't know how you call it, one revolution, I guess, whatever is the formal word. How would you know? How would you explain that it's 3 minutes to someone? Oh, okay. There we got a contribution there. Because it goes back down to the start at the 3 minute mark. That is deep. So we're paying attention to where the wave first started down here. So it started right here at 0 minutes. Let's just say that's zero. And it ended back to that initial Y value. I guess we'll call it the initial output after 3 minutes. So take a look. It started at zero, ended at three. So we're looking at where it starts and where it ends. Those 2 points. Now that's making me think, is that what Danny meant when you had that question? So those 2 points, that is accurate. Yeah, we're looking to see where we go back to our initial position. That's one way to measure the period, which is an awesome way. The period of this Ferris wheel is indeed 3 minutes, as you all said. And I'm going to show you a strategy to find out the period of any wave without having a Ferris wheel. So what if I just gave you a random old graph and you have no idea how to find the period? I'm going to give you a strategy right now. Oh, and then Danny, you put, because it takes you 3 minutes to do everything possible. Like to do every output possible, right? That's how I'm interpreting it. Yeah. It takes you 3 minutes to do everything possible. And everything possible is basically what's happening here in this first wave. That's right. And basically the rest of them are just going to be a repeat, right? The repeat of everything possible. I like that. Okay, y'all. So, okay, we're in agreement that the length of one period for my Ferris wheel, 3 minutes. Let me show you the strategy though, Because when you have other waves that I'm going to show you, it's going to be difficult to figure out what the period is because you don't know the starting point. Sometimes we don't know, like, where did the rider board the Ferris wheel? You know, sometimes there's Ferris wheels where sometimes you board at the middle. You know, sometimes you board up here in the middle. You have to go up some stairs. I've seen funky Ferris wheels where you board at the very top, right? So it depends where you start, right? When you're trying to measure the period length. So here's the strategy, everyone. How to measure the period of a wave. Here's what you do. You measure, and maybe some of you remember this from physics, but what the strategy is, you measure the distance from one peak to another. See this distance that I just drew on here? If I know the distance of this line or what this line is measuring, that's going to tell me the distance of one cycle. And where the reasoning is coming for why this works, it's very similar to kind of what Brenda said, like where you start and where you end. It's very similar because it's like saying, how often does it take for me to reach a maximum again? That's going to be the length of your cycle. So, how do we apply this? Strategy, count the distance between two maxima. That's a formal way to say it, y'all. Maxima, two peaks. So what you're gonna see is, let me go ahead and clear my line, is a red line. So, okay, I counted the distance, but I do not know what that distance means. What you do is you take that red line, you're gonna use your x-axis as a ruler. So I'm gonna take that and I'm gonna put it down, see that? Down on my x-axis like a ruler. And if I were to measure this line on my x-axis, it's gonna end up at 3 minutes. That is the strategy, everyone. So it was, for some of you, it was pretty straightforward to look at this and say, well, I know that if I go on the Ferris wheel, I do one cycle in 3 minutes. But this is going to be the strategy. You're going to see how it's going to help us. Let's see what's on the chat. Oh, okay. So is there a formula? Yes. So that is basically the formula, counting the distance between two maxima. And let's do another practice. So I hope that helps. That is the formula. Yes. Let's do this again. Let's try it. Let's try some more practice. Oh, and then this is just me down here putting in the formal definition of a period. Just the fact that P in this case is 3 minutes. Okay, y'all. Oops. So actually, before we jump into another example for finding the period of a sinusoidal function, what I'd like to do is actually pause and see what you all think right now, actually, right now from what I just said, and then we're going to do some examples. Take a look. I want you to process what we just did. So explain the strategy for finding the period of any sinusoidal function. So what I just said right now, I'm going to put the Padlet in the chat, and let's go ahead and take some processing time right now. So feel free, and also like any clarifying questions and things like that, feel free to put that into the chat as well. I mean, into the Padlet. So we're going to open up Padlet. We will go to, well, once it loads, here at the school, the Wi-Fi isn't as fast as it was for me, so it's taking a bit to load. Okay, there we go. We are on column 4, everyone. In your own words right now, describe the strategy for finding the period of a sinusoidal function. So I just went over that. That was in slide number 11. So try your best to kind of, in your own words, express this. And then we'll have about a minute or two, and then we'll come back. Don't forget to put your name or initial. So I put the directions in the chat. In the Padlet. Describe the strategy for finding a period. Oh no, the link is not. Let me send it to you directly. Let me know if you could see it now. I'm gonna re-put the link in the chat again, everyone. There you go. And great, so I see Danny and I see Miles getting started on the Padlet. Let's go ahead and take 2 minutes here, and let's all jump on that Padlet and process what we understand right now. So in your own words, explain the strategy for finding the period of a function. All right, I see plenty of us are still taking their time to write. So let's go ahead and have another minute on column number 4. I'm seeing very great like descriptions in our own words on how we are finding the period. So let's be back in one more minute. All right, everyone, we are coming back. Um, we're coming back, and I just went ahead and I just highlighted different, like the things that were coming up that are different and our common theme. So let's go ahead and talk about those. So one of them I found as a common theme coming up is you look at your graph, you look at it, and you figure out how long it takes to complete a cycle. See, one full cycle, and then there's a mention about counting the distance between the maxima, which is that shortcut I showed you. Another one that I noticed, a common theme, is looking where the line goes back down to the x-axis. So just seeing where it kind of goes back to its starting position and then you'll know and you'll get the period of the function. Um, Something that was mentioned consistently and a lot is basically looking for a pattern. So I see pattern mentioned a lot. Strategy perhaps completely forgot. That's okay. We're going to do more examples, and or you could try and see if you can make sense of what we have here, of anyone's explanations. Again, I see pattern coming up. I highlighted this one because um, not only was pattern coming up, but a lot of you mentioned looking for when the function starts to repeat itself. Then that's how you know that's the length of one period. So I really like this strategy down there. Awesome. So I think I pointed out all the stuff that was different. If you feel like you actually said something that was different from what I've pointed out so far, let us know. Feel free to share. Um, but let's go ahead and transition back to some examples. So y'all have some processing done right here on what the strategy is. So let's try this out. We're going to go back on our slides, and I am on slide number, what is this, 13. Okay. So take a look. There's no Ferris wheel here or nothing. This is just a simple way for you. Notice how in this example, the input is basically radians down here on the x-axis, and then your height on the y-axis are just like kind of just ones, threes, four, and you also have negative numbers. The goal is to find the period of the function. Now for this, stick to your strategy if you feel like your strategy is actually helpful for you. I'm going to go ahead and use the shortcut strategy that I showed you all. So here's the strategy. You just choose two maxima that are right next to each other. So I already can see these two right here. So I'm going to go ahead and measure the distance between the two. And basically at home, if you're doing this at home, you could just use your fingers and be like, okay, so the distance is about this much. Then you ask yourself, well, how much is this much though? I just have this length and I don't know what it is. What you do is you take this length and you're going to use your x-axis as a ruler. Use your x-axis as a ruler. Let me type that down. And then you'll know the length of this segment. So I'm going to take this, bring it down, take a look. I just took that very same length and I brought it down to the x-axis. And the x-axis is acting like a ruler, and it's telling me that the red line has a length of 4 pi. It's telling me that. Therefore, everyone, the period of this wave is 4 pi, because that's exactly what it's telling me the measurement is. So remember, I'm using that shortcut strategy where I'm measuring the distance between two maximums, AKA two peaks, and then I'm using my x-axis as a ruler. So let's see. So that's the steps. Are there questions about this example? Okay, so I don't see any questions coming up, but if they do, definitely. So earlier, some of you did message me like, oh, I'm a little bit confused. So if that's still you, feel free to go ahead and see if these examples are still confusing and send me a message and maybe I could address it like that way. We as a whole class can talk about it. Let's do one more example before we hit the Google form. Oh, question was, do we do that with the y-axis if we need to find it? So it would be x-axis. So in this case, we're doing x-axis for that question that I was just asked. Let's do another example so you can see how I'm using the x-axis. Not necessarily the y-axis just yet. So let's do the strategy again. Okay, so I have this other graph. Notice how my input is again in radians right here, my x-axis. And notice how the y values are now negative down here. So that's just something to notice about this graph. Okay, cool. But to be honest, to find the period of a function, I just need to do the steps. So let's do it. I'm going to go ahead and find the distance between these two maximums. So I'm going to draw a line. So for you guys, the line is like your fingers. Just use your fingers to be like, okay, it's about this much. And what you would do is you take your fingers and move it up to the x-axis as a ruler. So here's my x-axis. Let me circle it. I am using x-axis as a ruler. Again, I'm going to type out what I'm doing. And I'm going to go ahead and just copy and paste that same line up here to tell me what my x-axis ruler says the length of that is. Now, oops, it went a little bit over, but what it is, it's actually, it should be exactly 2 pi. The length of this distance, which should be a little bit shorter, so I think I went a little bit past it, but anyways, the length should be 2 pi. So if you were to use your fingers and you just measure the distance between that and go to the x-axis as your ruler, you would see it ends up at 2 pi. So the answer to this question, find the period of the following, the answer is going to be 2 pi. The period is 2 pi. The period length is 2 pi. That is our answer for this problem. Now, let's see if there's questions. This was our last example before you hit the Google form to process your understanding. Now, let's see if there's questions. Someone asked something about y-axis, but yeah, we're using the x-axis. Let me see if there's any other additional questions. Okay, I don't see any questions coming up now. So let's go ahead and just process our understanding with a Google form. The Google form will be for your credit, so participation credit. Remember, it's not a judgment. It's more so you check your understanding. So that's what the Google form is, and you get credit. You get an A. Okay, if you're, yeah, so if you're still stuck, go ahead and try out the Google form. And that way I'm able to see where specifically you're stuck at. So is it at the Ferris wheel part? Is it at the finding the length of a period? And, you know, we could work on that. And also I'd be happy to work with you on office hours. So my office hours is going to be Thursday, everyone. Thursday at 2 for this week. Be very glad to help us all. So yeah, I want to acknowledge some of you are like, I got this. And you know, yo, I can't do anything. I can't whistle. I can't snap my hands. What can I do? Okay. And I'm even wobbly on a bike. So anyways, some of you got it like this. Just pretend I am able to do that. Some of you got it happy. Some of you look like this. You're stuck and you're still trying to make sense of this. That both of these are perfectly fine. They're perfectly legit. You're in class. And if you're stuck right now, that means right now you're trying your best to engage your brain in this and it's hard. So I want to acknowledge that. And again, I want to acknowledge that this is more so to see where you're at, both for me and for you. So let's go ahead and do this Google form in the next 10 minutes, and then I'm going to come back and bring us back. Of course, of course. Here's our Google form. I put it in the chat, everyone. If you're on the slides, you know, feel free to take a look. We're going to be having, we can't have the next 10 minutes. It's going to have to be the next 7 minutes. So 7 minutes, because that's how much time we have in class. So go ahead and complete this Google form in the next 7 minutes, y'all. Do y'all know that my in-class credit is worth as much as asynchronous assignments? Do y'all know that? Please do this Google form because it's going to be as much as an asynchronous assignment. I started the timer so y'all can get started. Wait, fake it till I make it. So it's okay if you're stuck. Don't fake it. So be honest at where your misunderstandings are at. But yeah, the in-class stuff that we're doing is worth as much as asynchronous. So please do this form. It's worth a lot of credit. So please do it. All right. All right, so y'all, I'll see you in about 6 minutes. Go ahead and fill out this form. All right, everybody, welcome back. So I'm gonna make sure I send the form again, a reminder. I do not want any of you to miss your credit, but if you're still working on it, please do. If you're nearly there and just have a few things, just make sure you submit something for your credit today. 100% as long as you submit it, you get an A. So y'all have an amazing lunch. And yes, you can make up any Padlet responses. Yes, you can do that. If anyone's missing your Padlet credit, please, you could go back and make up any of them. Okay, everyone, I gotta go ahead and end this meeting. See you all. Enjoy your lunch. Turn in that form. Bye, everyone.
All right, see ya.
Bye.
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 Bye-bye.